In section 7.3, we're going to be proving some trigonometric identities. Our objectives are to prove identities using other identities. And also we're going to get some new identities, the product to sum identities and the sum to product identities. We're going to use these to derive others. Quick review. What do we mean when we say we've proven something in everyday language? So when we prove something, we want to demonstrate that it is true. So how is proof used in mathematics? If we're trying to prove an identity, we want to show that both sides of the equation or identity are always the same or are equal to each other. Show that both sides of an identity are equal for all values of x. Okay. And that usually means working the two sides out until they are the same. So in other words, we want same on both sides. All right. Since all of our identities are equations, we are going to try to manipulate one side of the equation until it becomes the expression on the other side. There's no one straight process that's going to allow us to do that every time. Instead, we've got some tips for proving identities. One of those tips is to choose a side of the equation to work with and stick with it. Then you're going to write down the other target side and try to take that one equation and work it until you can get the target side. Keep a running list of which you've done, i.e. which identities you've used for later reference. It helps to just write down a quick note so that you can go back before an identity or can reprove this looking up the identities that you used. Okay. You also want to start with the side that is more complex and try to simplify that side. When you're trying to choose a side that's more complex. You want to carry out any obvious algebraic manipulations, i.e. adding, subtracting, factoring, combining like terms, etc. You also want to rationalize and or find common denominators when possible. If there aren't any algebraic steps to do, you might try converting things into just sines and cosines. So moving away from tangent, cotangent, secant, cosecant. You also might need to consult the target side to look for possible clues on what to do next. And just keep trying. Keep playing around with things, even if it means starting over and trying another route. You may have to do that if your path is not leading you in the direction you were hoping it would. All right. My next piece, it says, let's start by listing as many identities as we can to begin. So I'm not going to be able to list the entire identities on this page, but let's think about our reciprocal. So that would be things like sine of x equals 1 over cosecant of x, etc. So we have our reciprocal identities. We have our basic identities, such as tangent of x equals sine of x over cosine of x, and so on. We have our Pythagorean identities, such as sine squared x plus cosine squared x equals 1, and so on. You have the ones for tangent, secant, cosecant, and so on. So I'm just writing down right here the types of identities to look for. We have our reciprocal identities, our basic identities, our Pythagorean, which I should probably just write the whole word, Pythagorean. Pythagorean identities. Sorry, Pythagoras, I spelled his name wrong at first there. We've got our Pythagorean identities. We've got our sum and difference identities. That's our sign of u plus v equals, etc. I'm not going to write that whole identity down, it's long. So we've got our sum and difference identities. We've got our double angle identities. That's our sign of 2x equals, and we've got our half angle identities. And that would be our sine of x over 2 and cosine of x over 2. I'm just abusing sine here and writing those down, but you're going to want to make sure you look at all of those. So giving some examples of what they look like. But of course, there are lots of types of identities that we've already seen in this chapter. So take a look at your formula sheets or look in your book for reciprocal, basic, Pythagorean, sum, difference, double angle, and half angle identities. You're going to want to have a list of those handy as you begin proving your trigonometric identities. Okay, so in this first identity to prove here, I look at it, I see I've got secant of x minus sine of x times the tangent of x, and it's equal to cosine of x. So I'm going to figure out which side to work on, and I want to pick the side that's more complicated. So we're going to work on that left-hand side in this one. And then the goal, the thing that I'm going to try to get that left-hand side equal to, is going to be cosine of x, right? That's going to be my goal. So we're going to start with secant of x minus sine of x times tangent of x. I got to get that turned into cosine of x to prove this identity. I need to get both sides to be the same, so I'm going to work on that left-hand side and make it equal to the right-hand side through the use of identities. Okay. Well, one thing that I can think to do is starting with the reciprocal and basic identities. So I'm going to try to get this into sines and cosines, which is one of our tips from the previous page. So I'm going to make a note here that I'm going to be using reciprocal and basic identities. And I'm going to turn the secant into a 1 over cosine. And then I've got my sine of x doesn't need one. It's already one of the standard functions. But tangent, I'm going to use the basic there. So reciprocal, that was for secant. The basic one for tangent is that tangent is equal to sine x divided by cosine of x. Okay, so that was using identities. I'm going to rewrite without an identity, just combining algebraically. Sine of x times sine of x gives me sine squared x over cosine of x. And I've got a common denominator, so I'm going to subtract the numerators and have 1 minus sine squared x over cosine x. So if you need to keep track of the identities that you've used, you can. So for the reciprocal, since they're so standard or basic, I don't need to write them down every time since I know these ones and I've said what I'm doing over here, but I'm going to write them just for emphasis. The one I used here was that secant of x was equal to 1 over cosine x, and the other one that I used was the basic tan of x equals sine x over cosine x. So I would say for those two, making them in a list right here is optional since most of us know those without having to look them up. I would definitely list in the list of identities that I'm using my next step right here. I've noticed that I've got a sine squared and I've noticed that I've got a 1. And so I'm thinking that those are going to work well together with one of the Pythagorean identities. And this one is sine squared x plus cosine squared x equals 1. So the next thing I'm going to do is apply that Pythagorean identity. There's a couple of different ways that I can apply it. I can sub in for the 1, the full sine squared x plus cosine squared x equal to the 1. Or I can subtract the sine over, and I can write this identity as cosine squared x equals 1 minus sine squared x. And that's actually the form I'm going to use right here. I've got myself a 1 minus sine squared x by the Pythagorean identity that is equal to cosine squared x. So I've got cosine squared x over cosine x. That step happened based on one of the Pythagorean identities. And then from there, we're going to reduce. So cosine squared reduces out with cosine and leaves me with a single cosine of x. Remember that my goal was to get this to be cosine of x, and so I have accomplished that goal. I've worked just on the left-hand side using identities. I used 3 different identities as well as some algebraic manipulation to show that it was equal to the right side. So on the left side, it's equal to cosine x, and the right side is equal to cosine x. So these functions are equivalent for all values of x. Okay. Let's take a look at another one. I've got a 1 plus tan y over a 1 plus cotan y. It's supposed to equal secant of y over cosecant of y. I'm going to start with the side that I consider to be more complicated. That's going to be the one that not only has a fraction, but has the addition. I'm going to work on that left-hand side again with the goal of getting this to equal secant y plus divided by cosecant of y. Again, that's going to be our goal. So working on the 1 plus tangent of y over 1 plus cotangent of y. Well, I need to get secants and cosecants, not tangents and cotangents. So perhaps one of the first things I could do here is go into sines and cosines using some of my basics. So we know that tangent of x is equal to sine x over cosine x, and conversely, cotangent x is equal to cosine x over sine x. So let's use those basics. To write this as 1 plus sine, the variable here is y, so sine y over cosine y over 1 plus cotangent, that's going to be cosine y over sine y. So use a basic identity. It looks a little messier now, but I have stacked fractions and I can get rid of those using common denominators. This is not an identity, it's an algebraic technique. So for common denominators, we know that we're going to multiply both top and bottom by the common denominator. The common denominator is going to have both cosine and sine. So I'm going to multiply by sine of y times cosine of y, top and bottom. Sine of y, cosine of y. This will need to be distributed. across the top and the bottom. 1 times sine of y cosine of y will be sine of y cosine of y here, plus the sine of y times the cosine of y. I can imagine that when I multiply these together, the cosine of y is going to cancel with the cosine of y in that term only. And it's going to leave me with sine of y times sine of y, or sine squared of y. On the bottom, 1 times the sine of y cosine of y is going to give me the sine of y times the cosine of y, plus here the sine of y is going to cancel, and that's going to leave me with the cosine of y times the cosine of y, so that is the cosine squared of y. So distributing allowed me to get rid of the fraction, but I might now want to refactor this. So we're going to come up here. There is a sine y in common across the top, and I would have cosine of y plus sine of y left if I factor that out. And across the bottom, both of these terms have cosine of y. And I would have a sine of y plus a cosine of y left if I were to factor that out. The binomial cosine of y plus sine of y and sine of y plus cosine of y, they're additions. So the order doesn't matter since they're both plus. So those are the same, and that is going to reduce. Cosine of y over sine of y is going to reduce with the sine of y plus cosine of y. So again, that's just an algebraic step. Those reduce. And so what I end up here is sine of y over cosine of y. Now, that's not what I want, but I'm going to look for clues. What I want is the secant of y over the cosecant of y. So let's try to use reciprocal identities here. We know that the sine of y is equal to 1 over the cosecant of y, and the cosine of y is equal to 1 over the secant of y. So we're going to apply those reciprocal identities. Sine of y is 1 over cosecant of y, and cosine of y is 1 over secant of y. Now I can use properties of fractions to write this as 1 over cosecant of y times the reciprocal, secant of y over 1. So I end up with secant of y over cosecant of y, and that's what I was trying to get. Got a little messy here. Sometimes a little extra paper and space would just be helpful for this organization, but I was able to show that I can take this left side and transition all the way to exactly the right side, which was our goal. We ended up using only basic and reciprocal identities. Reciprocal identities really are basic identities as well. And then some algebraic manipulation, distributing, factoring, common denominator, all of those techniques. Okay, let's try another one. Ooh, we've got a whole page. Excellent. So example 3, we need to prove the identity. Well, there's a lot going on here, but I can tell that the side that is more complicated is the left-hand side. So I'm going to try to work through that side. It's got powers, it's got subtractions, it's got a lot more functions than the right-hand side. So once again, the goal is going to be the other side, which is the side that looks to be simpler. It's not always the left-hand side that you're going to start with. It just happens to be the way these questions were printed, that they had their left-hand sides where a more complicated function was living. So we're working with the function cosine cubed of x minus sine cubed of x over cosine of x minus sine of x. And we don't have an identity that has a cube in it. We've got sine squareds and cosine squareds, but I don't have anything for power 3. Instead, I'm going to think about a factoring technique for cubes. So we can factor a difference of cubes using the formula that a cubed minus b cubed will factor into a minus b times a squared plus ab plus b squared. In this case, I do have the difference of two cubes. The a, the thing that's cubed first here, is cosine of x, and the b is sine of x. So let's get this factored. When we factor, cosine cubed x minus sine cubed x is going to factor as a minus b, so that's going to be cosine x minus sine x times a squared, so that's cosine squared x, plus ab, so that's cosine x, times sine x, plus b squared, so plus sine squared x. And it's still here divided by cosine x minus sine x. Now that we've factored, we can take a look at what we've got, and we can see that the binomial cosine x minus sine x is going to reduce with the denominator. That's the same there. So this simplifies as cosine squared x plus cosine x sine x plus sine squared x over 1. So we just have that trinomial portion of our factoring here. Now that I don't have a cube and I have sine squareds and cosine squareds, I might think of the Pythagorean identity that says that sine squared x plus cosine squared x is equal to 1. And I do here have a sine squared x and a cosine squared x. So if I apply that Pythagorean identity, I can substitute sine squared x plus cosine squared x equals 1, plus the cosine x times the sine x. So we've got quite a bit in terms of simplifying here. Now we're going to look back at our goal. Our goal is to make this look like 2 plus sine of 2x over 2. So the first thing I might do is create that fraction. We're going to put this over 1. And then we're going to multiply just top and bottom by the number 2 so that we have it in that same form as our goal here. This is 2 plus 2 cosine x sine x over 2. Now the initial 2 and the 2 in the denominator are both exactly matching our goal. We just need the sine of 2x. And I don't have that yet here, but since it is the sine of 2x, that it's my goal, I might look up the double angle identities and find that the sine of 2x is equal to 2 times the sine of x times the cosine of x. And I have 2 times cosine x sine x, that's the same thing here. So I'm going to sub in that double angle identity. So I have 2 plus the sine of 2x over 2. And that's exactly what I was trying to get. So we have achieved the goal here. All right, on the next page, we're looking now at the product to sum and sum to product identities. So these are identities for taking things that are either the product of two different angles, so the sine of x times the sine of y, and making them either a sum or a difference of a singular angle, that is the difference or sum of the two angles in the product. That's our product to sum identity. Or we can do the reverse and we can take a sum to product identity, take the sum of two separate angles and turn it into the product of different functions, sine and cosine here, of angles that have been added or subtracted from the angles that I have started with. Let's take a look at one of these in an example. Our goal is to convert the sine of 7 beta minus 4 beta into a product. So this is currently a difference. So we're going to start with the sine x minus sine y. That's the format that we have right here. It's not a sum, it's a difference of signs. And we're going to turn it into the 2 times the cosine of x plus y over 2 times the sine of x minus y over 2. Okay. So our sine of 7 beta minus the sine of 4 beta turns into 2 cosine of x plus y. In this case, x is 7 beta plus y is 4 beta over 2 times the sine of x minus y. So 7 beta minus 4 beta over 2. And we get 2 times cosine of 7 plus 4, that's 11 beta over 2, times the sine of 7 minus 4, that's 3 beta over 2. So this would be our simplified version in terms of a product now instead of the difference we started with. One potential use of this formula is if you're solving an equation where you have different angles and can't combine those two functions. Sometimes converting it into a product puts it in factored form. If you had it equal to 0, you'd be able to continue solving this. Just one potential use of this identity. In this case, we just wanted to rewrite a product, and that's as far as we can go. In example 5, we're going to use an identity to convert 7 times the cosine of 5 theta times the cosine of 7 theta into a sum or difference. This right here is the product of two cosines. So that's going to be the second line here, the product of two cosines. We're going to turn that into 1/2 the cosine of the difference plus the cosine of the sum of those two angles. So 7 cosine of 5 theta cosine of 7 theta will turn into 7 times 1/2. That's going to be 7/2. 7 times 1/2 cosine of the difference. So the difference of the two angles will be 5 theta minus 7 theta plus cosine of the sum, 5 theta plus 7 theta. And let's simplify that. 7/2 times the cosine of 5 minus 7 is negative 2 theta. And then the sum, 5 plus 7, is going to be 12 theta. Oops, there we go. We're almost done on this one. The last thing to do is use the property of cosine, that cosine is even, to simplify the cosine of that negative angle right here, using the fact that cosine is an even function. Doesn't show up very well, so let me rewrite that. Cosine is an even function. So that means that the cosine of negative 2 theta is the same thing as the cosine of positive 2 theta plus our cosine of 12 theta. So that angle was not really fully simplified as the negative, but it can be simplified as now as written as a positive angle. All right. And also just wanted to think about this one. This is my answer here. Also wanted to think about the fact that the order of that multiplication truly didn't matter. So I could have written this as 7 cosine of 7 theta times cosine of 5 theta. In that order, this difference would have come out as 7 theta minus 5 theta, which is 2 theta. So just another way of illustrating that that really should come out as a positive 2 in our final answer. Okay. Let's look at our last page here. We've got one more identity to prove. And this one, we've got the tangent of x plus y over 2. And we want to show that this is equal to the sine of x plus the sine of y over the cosine of x plus the cosine of y. In this example, I would say that the right-hand side has a little more going on than the left-hand side. It's got 4 different functions, and it also has different angles, angle x and angle y. So I'm going to work on that right-hand side with a goal of getting to the left-hand side, which is the tangent x plus tangent y over 2. So this time, my goal is going to be to get from the right side to the left side. So I'm going to start manipulating the sine of x plus the sine of y over cosine of x plus cosine of y. I'm adding 2 separate sine functions with different inputs and adding 2 separate cosine functions with different inputs. So we're going to use those sum to product identities. We're going to be working on these sum to product identities using the sine x plus sine y and the cosine x plus cosine y down here. So let me write down the identities we're using. We're using sum to product. So from our previous page, the sine x plus sine of y is going to turn into 2 sine of x plus y over 2 times cosine of x minus y over 2. Again, that is the identity for the sum of the sines. Now we're going to use the identity for the sum of the cosines. So we're going to get 2 times the cosine of x plus y over 2 times the cosine of x minus y over 2. Just a quick note about this. This is written in the order cosine y plus cosine x. There's nothing really special about why it's written that way. Since addition can be written in either order, this could be written as cosine x plus cosine y, and it's still equal the way it was read because we can add things in either order. So I'm not sure why it has those flipped. It might matter in terms of the difference, of course, because in the difference, sign matters, but it doesn't matter in terms of the sum. So I just wanted to pay attention to that. I didn't want to ignore it completely, but mine has cosine x plus cosine y, and when you're adding, you can switch the order of addition without any change or consequence in the equation. All right, so we've done that. And now we can see that we can reduce. The 2's here are going to reduce. And we're also able to reduce the cosine of x minus y over 2's. So it looks like what I have left here after reducing is the sine of x plus y over 2 divided by the cosine of x plus y over 2. And since these angles are the same, we're going to be able to make use of the basic identity that says that the tangent of any angle is equal to the sine of that angle over the cosine of that angle. And that angle happens to be x plus y over 2. So with that basic identity for tangent, this is going to be equal to tangent of x plus y over 2. And if you look back, that is the goal. That is what we were trying to show that we were equal to. So we were able to show that both sides are the same, and we've proven this identity.